Welcome. There is nothing to do now but rest. Let your breath slow. Let your shoulders sink into whatever is holding you. Nothing here needs your attention, only your ease. Tonight we drift back through the long story of how a small, curious species first looked up and dreamed of reaching the stars. Ancient civilizations charted stars for navigation. Sailors and shepherds alike traced patterns overhead, turning scattered points of light into maps for crossing oceans and deserts. Isaac Newton's laws of motion enabled spaceflight theory. In the 1680s, a quiet Englishman described how objects move and how forces balance, without ever imagining a rocket. His three simple laws would later explain exactly how a vehicle could push against nothing and still be carried forward. Centuries passed before anyone applied his equations to the empty dark above the clouds. The stars, patient as ever, waited. Konstantin Tsiolkovsky formulated the rocket equation in 1903. Working alone in a small Russian town, deaf since childhood from illness, he calculated how a rocket's speed depends on the fuel it burns and casts away. His equation still governs every launch today. He imagined space stations and interstellar travel decades before anyone built a working rocket, sketching his visions quietly by lamplight. Robert Goddard proposed liquid-fueled rockets in 1926. On a frozen New England morning, his small rocket rose only a short distance, yet it proved that liquid propellant could lift a craft skyward. Newspapers mocked the idea at the time. Goddard kept building anyway, unhurried, certain that something larger was taking shape in the cold Massachusetts air. Hermann Ober theorized interstellar travel in 1929. A German physicist, inspired by early science fiction, wrote calculations describing how rockets might one day cross the space between stars, not just planets. His work read like a bridge between imagination and physics. It would take generations before his numbers found their way into real machines. The V-2 rocket demonstrated liquid propulsion in 1944. Built in wartime Germany, it became the first human-made object to reach the edge of space, rising far above the clouds before falling back to Earth. Its technology, born from conflict, would later be repurposed for peaceful exploration. History moved forward on unlikely paths. Sputnik 1 became the first artificial satellite in 1957. A simple metal sphere, smaller than a beach ball, it circled the Earth every 96 minutes, sending a steady radio pulse into the dark. People around the world stepped outside at night just to watch its faint light cross the sky. A new era had quietly begun. Yuri Gagarin became the first human in space in 1961. For 108 minutes, a young pilot orbited the Earth alone, watching continents drift beneath him in silence. He later said the planet looked impossibly blue and fragile from that height. It was the first time a human heart had beaten so far from home. Apollo 11 landed humans on the Moon in 1969. 2 astronauts stepped onto gray dust that had waited undisturbed for billions of years. Their footprints remain there still, untouched by wind or rain, because the Moon has neither. Overhead, Earth hung silently in a black sky, the only splash of color in the whole scene. Pioneer 10 launched toward Jupiter in 1972. It became the first spacecraft to cross the asteroid belt and the first to fly past the solar system's largest planet. After its brief encounter with Jupiter's swirling clouds, it kept moving outward, quietly leaving everything familiar behind, drawn only by the pull of the space beyond. Let your breath find its own rhythm now, without any effort to shape it. Notice how each exhale stretches a little longer than the one before, releasing a small piece of the day each time. Air fills you, then leaves you lighter, looser, more settled into the mattress beneath you. This rhythm is older than any spacecraft, older than any star chart ever drawn. It is simply yours, and it is enough to carry you toward rest. A golden plaque rides aboard Pioneer 10, engraved with the outlines of a man and a woman standing side by side. Beside them, a diagram traces Earth's location using pulsing signals from distant pulsars, a kind of cosmic return address. Its designers hoped that if another intelligence ever found the drifting probe, they might read where it had come from. The plaque remains bolted to its frame, carrying a quiet message meant to outlast everyone who made it. Its twin, Pioneer 11, left Earth in '73, bound for the outer planets that Pioneer 10 had already begun revealing. It went on to become the first spacecraft to fly past Saturn, threading carefully through the gap in its rings. Instruments recorded magnetic fields and radiation belts no human eye had ever measured. Like its sibling, it now travels outward, alone, somewhere in the space between the stars. Project Daedalus imagined a starship, driven by tiny fusion explosions, ignited thousands of times each second behind a massive engine bell. Engineers at the British Interplanetary Society spent 5 years shaping the design, publishing their work in '78. It existed only on paper, yet the detail was extraordinary: fuel tanks, sensors, even a plan to reach Barnard's star within about 50 years. No metal was ever bent, but the study proved such a journey could at least be imagined in careful numbers. Voyager 1 left Earth in '77, launched toward Jupiter and Saturn on a mission meant to last only 4 years. Its cameras and instruments were built to study clouds, moons, and rings up close, sending images back across the widening distance. No one expected it to still be traveling and reporting decades later. Its long silence between transmissions was the first hint of how far it would eventually go. Its counterpart, Voyager 2, followed just weeks earlier that same year, set on a wider path that would eventually carry it past Uranus and Neptune as well. Engineers arranged its route to take advantage of a rare alignment of planets, a grand tour that would not repeat for well over a century. Together, the two spacecraft would rewrite what was known about the outer solar system, moon by moon, ring by ring. The Voyager Golden Record carries the sounds of Earth into the dark, a phonograph disc etched with music, greetings, and the calls of whales. Engraved instructions on its cover show how to play it, meant for whoever might one day find it. Photographs of forests, cities, and human faces are encoded in its grooves alongside a heartbeat and birdsong. It travels now farther from home than any recorded sound has ever gone. Voyager 1 crossed into interstellar space in 2012, becoming the first human-made object to leave the sun's bubble of influence entirely. Instruments detected the density of surrounding plasma rise sharply, confirming it had passed beyond the heliopause. It was already billions of miles from the launch pad it had lifted off from decades earlier. Its faint signals still crossed the dark toward Earth, taking more than 20 hours to arrive. Contact with Pioneer 10 was lost in 2003, its radio signal finally fading past the reach of Earth's antennas. By then, it had traveled for more than 3 decades, its power source weakening with every passing year. Engineers listened for one last faint reply, but none came. It continues outward still, coasting toward the constellation Taurus, carrying its golden plaque toward stars it will never reach. In 2006, a piano-sized spacecraft named New Horizons lifted off toward the edge of the solar system, aimed at a small icy world once counted as the 9th planet. It carried a small container of ashes from Clyde Tombaugh, who had discovered that world 76 years earlier. Traveling faster than any spacecraft before it, New Horizons would spend 9 years crossing the emptiness before finally nearing its target. 9 years after leaving Earth, New Horizons swept past Pluto in 2015, capturing the first close images of its frozen surface. Nitrogen ice plains stretched beneath a pale sun, and mountains of water ice rose along the horizon. The flyby lasted only a few hours, gathered at tremendous speed. Data trickled back to Earth for more than a year afterward, each transmission carrying fragments of a world once seen only as a blurred point of light. Feel the weight of the evening settle into you now. Your shoulders grow heavy against the mattress, then your arms loosen, one by one. Your hips sink lower, your legs grow dense and still, as though the bed were rising to hold you. Your head rests fully into the pillow, its weight no longer yours to carry. Each breath presses you a little deeper into stillness. New Horizons left Earth faster than any spacecraft before it, accelerated to over 36,000 miles per hour by its rocket alone. It needed no gravity assist to escape Earth's pull outright, though it still used Jupiter to bend its path and gain speed toward Pluto. That initial burst of velocity meant it crossed the orbit of the Moon in just 9 hours, a distance that took the Apollo missions 3 days to cover. Breakthrough Starshot was announced in 2016, a project seeking to send tiny probes toward another star system entirely. Physicist Stephen Hawking stood among its early supporters, lending the idea public attention rarely given to interstellar concepts. Funded initially with $100 million, the project set out to explore whether light itself might carry a spacecraft across the stars. Its ambitions were modest in size but vast in scope. Project's ultimate goal is to reach the Alpha Centauri system, our nearest stellar neighbor, within a single human lifetime. Its design imagines a fleet of gram-scale sails, each thinner than a soap bubble, pushed by concentrated laser light from Earth. No fuel would be carried aboard. The push would come entirely from photons striking a mirrored surface. Reaching such speeds remains far beyond current engineering, though the physics behind it holds together. Alpha Centauri is the nearest star system to our own, a trio of stars bound together by gravity across the southern sky. Two of its stars, Centauri A and Centauri B, orbit each other closely, resembling a pair of suns, locked in a slow dance. The third, a dim red star named Proxima Centauri, drifts farther out, closest of all to Earth. Ancient sailors in the southern hemisphere once used its light to find their way home. About 4.37 light-years separate Earth from Alpha Centauri, a distance that sounds small only beside the emptiness surrounding it. Light leaving that system tonight would take over 4 years to reach us, arriving long after it departed. At the speed of today's fastest spacecraft, the journey would stretch across tens of thousands of years. Even our nearest neighbor among the stars lies impossibly far by any ordinary measure of distance. Proxima Centauri, the dimmest of the three, holds a small rocky planet in close orbit, discovered in 2016 and named Proxima b. It is roughly the size of Earth, circling its star far closer than Mercury circles the Sun. Because Proxima Centauri burns cooler and dimmer than our own star, that tight orbit still allows for moderate warmth. It remains one of the closest known worlds beyond our solar system. Orbiting within its star's habitable zone, Proxima b sits at a distance where liquid water could theoretically persist on its surface. Whether it truly holds oceans or an atmosphere remains unknown, since red dwarf stars often bathe nearby planets in flares and radiation. Astronomers studying its orbit have not yet confirmed an atmosphere at all. Its position alone has made it one of the most discussed worlds in the search for life beyond Earth. 7 Earth-sized worlds circle a single small star in the system known as TRAPPIST-1, discovered through careful dimming patterns in its light. Each planet was found as it passed in front of its star, subtly lowering the light astronomers measured from Earth. From the surface of one such world, neighboring planets might appear larger than the Moon does from Earth. 3 of the 7 orbit within a zone where liquid water could theoretically exist. 40 light-years lie between Earth and a small, cool star called TRAPPIST, one far enough that its light left home before most living memory began. Around it circles 7 Earth-sized worlds, tucked close together like siblings sharing a porch light. No spacecraft built today could reach them within a human lifetime. Even so, astronomers study their shadows across that star with patient, careful attention. Between every star drifts a thin haze of gas and dust, so sparse that a single spoonful of it might contain only a few atoms. Astronomers call this faint material the interstellar medium, and it fills the spaces where nothing else seems to be. It shapes new stars, seeds future planets, and slowly drifts across unimaginable stretches of time. Nothing about it feels empty once you consider how much it quietly holds. Somewhere beyond the window, a low hum settles into the walls, the kind a house makes when it finally rests for the night. It rises for a moment, then fades, like breath drawn and released. There is no need to listen closely, no need to name it. Let it come and go, the way distant sound always does, asking nothing of you at all. Cosmic rays, streaming through space at tremendous speed, carry enough energy to pass straight through solid metal. For any craft crossing interstellar distances, this radiation becomes a constant, invisible companion. Engineers studying long journeys must plan for hulls that can absorb or deflect these particles over many years of exposure. It remains one of the most persistent hazards, weighed against the dream of traveling far. Dust grains scattered through interstellar space seem small enough to ignore, some no larger than smoke particles drifting through a room. Yet, at the speeds a starship might travel, even these tiny fragments could strike with tremendous force. A single grain, moving fast enough, might punch through metal the way a pebble tears paper. Designing shielding against something so small has proven surprisingly difficult. In the years following the Second World War, a group of physicists began studying a strange idea called Project Orion. Their proposal imagined a spacecraft propelled not by chemical rockets, but by a rapid sequence of controlled nuclear detonations pushing against a massive rear plate. On paper, the concept promised speeds far beyond anything achievable otherwise. It never left the drawing board, but it opened a door that engineers still glance through. The plan behind Project Orion called for detonating small nuclear charges just behind the ship, one after another, each blast shoving the craft forward, like a series of gentle taps from something enormous. Engineers calculated it could theoretically reach a meaningful fraction of light speed. Concerns about radiation and international treaties eventually closed the project. Still, its bold arithmetic has quietly influenced propulsion thinking ever since. Fusion propulsion, the joining of atomic nuclei to release tremendous energy, remains entirely theoretical for interstellar travel. Physicists have modeled fusion drives capable of extraordinary speeds, yet no working engine has ever flown. The technology to sustain controlled fusion reliably, let alone harness it for thrust, still eludes engineering reach. It stays a promising idea, waiting patiently for the right breakthrough. Antimatter, when it meets ordinary matter, releases more energy per unit of mass than any other known reaction. A propulsion system built around it could, in theory, carry a starship to relativistic speeds using astonishingly little fuel. Physicists describe it as the most energy-dense fuel imaginable. The universe, it seems, rarely offers such power without demanding something difficult in return. Producing even a tiny amount of antimatter currently requires enormous particle accelerators and vast sums of money, yielding only the faintest trace after enormous effort. The entire supply humanity has ever created could scarcely power a light bulb for a few minutes. Storing it safely presents its own quiet challenge, since it destroys itself on contact with ordinary matter. For now, the idea remains far ahead of what our hands can build. Sunlight carries no mass, yet it pushes, Photons striking a mirrored surface transfer a small momentum with every bounce, and a sail built wide and thin enough can ride that pressure like a leaf on wind. It will never rival a rocket's roar, but it needs no fuel tank at all. Given enough time, that patient push can carry a craft to speeds no chemical engine could match. Ground-based lasers offer a far stronger push than sunlight alone. Engineers have proposed arrays of thousands of synchronized beams, aimed skyward and focused onto a sail no larger than a postage stamp. The combined force could shove that tiny craft to a meaningful fraction of light speed within mere minutes. Once the beam switches off, the sail simply coasts, carrying its speed onward through the dark for years. Breakthrough Starshot, announced by physicist and philanthropist backers in 2016, imagines probes so small they fit in the palm of a hand. Each starship would weigh only a few grams, little more than a large postage stamp with electronics etched inside. Thousands could launch together, riding sails pushed by laser light toward Alpha Centauri. The ambition is enormous. The vessel itself is almost nothing at all. Let warmth begin at your feet now, spreading upward like sunlight moving across a floor. Feel it settle into your ankles, then rise gently through your calves, loosening what the day left tight. Let it climb to your knees, your thighs, filling each muscle with a slow golden heaviness. Let it rest there a moment, unhurried, before it continues upward through your hips, your chest, your shoulders, until every part of you feels warm, heavy, and ready for sleep. Each Starship probe, despite its tiny frame, would carry a miniature camera, a set of sensors, and a small radio for sending its findings home. Engineers imagine it capturing brief images of the Alpha Centauri system during a fleeting flyby, lasting only moments. There would be no time to slow down, no chance for a second look. Whatever it sees once, then races onward into the dark beyond. To push a sail toward relativistic speed, the laser array behind it would need to output power on the scale of gigawatts, comparable to a large power plant running at full capacity. Sustaining that output for the few minutes of acceleration demands an enormous energy reserve, carefully stored and released in a controlled burst. No such array exists yet. The concept waits for engineering to catch up with the arithmetic, already worked out on paper. Move fast enough, and time itself begins to behave differently. A traveler moving near light speed would experience the passage of years more slowly than someone left behind on Earth. The effect, called time dilation, has been measured on ordinary jets and orbiting satellites, confirming what relativity predicted. At a true starship's velocity, the difference would grow large enough to notice within a single voyage. At 1/5 the speed of light, a probe could cross the gap to Alpha Centauri in about 20 years. That is a span within a single human lifetime, remarkable when measured against the 4 1/3 light-years of empty distance between the stars. No spacecraft built so far has ever approached such velocity. Reaching it would mean crossing a threshold humanity has only imagined until now. Even traveling at the speed of light, a message from Alpha Centauri would take more than 4 years to arrive at Earth. A question sent outward and its answer returned would together span nearly 9 years of waiting. Mission planners must design for a conversation stretched thin across time, patient by necessity rather than by choice. Every signal becomes a small letter written to a future self. A probe moving at a meaningful fraction of light speed stretches and compresses the very radio waves it sends home. A shift caused by its motion, much like a passing train's changing pitch. Engineers call this effect Doppler shift, and at relativistic velocity it becomes severe enough to distort transmission frequency significantly. Receivers on Earth would need to constantly adjust their tuning to keep pace with a signal racing away or rushing past. Catching that fleeting whisper of data would demand instruments of remarkable precision. In the 1960s, physicist Robert Bussard imagined a starship that never needed to carry its own fuel. His ramjet design would scoop up hydrogen atoms drifting through interstellar space, using a vast magnetic funnel to gather them as fuel for fusion. The concept remains unbuilt, and engineers still debate whether the drag of collection would ever be overcome by the thrust it produced. Even so, the idea reshaped how people pictured a self-sustaining voyage. Efficiency, not raw power, defines ion propulsion. It works by charging particles of gas and accelerating them out the back of a spacecraft with electric fields, producing thrust so gentle it feels almost imperceptible. Over months and years, that whisper of force builds into enormous changes in velocity. Engineers prize it for missions where patience outweighs urgency, trading haste for a longer, steadier push. Dawn carried this quiet technology into practice. Launched by NASA in 2007, the spacecraft used ion engines to visit both Vesta and Ceres, two distant bodies in the asteroid belt. No previous mission had orbited two separate worlds beyond Earth, and its thrusters ran for years rather than minutes. Dawn proved that a gentle, sustained push could carry a machine across vast, looping distances with remarkable precision. Heat, applied at the right moment, could shorten a journey considerably. Nuclear thermal propulsion works by using a reactor to superheat propellant, expelling it at speeds far greater than traditional chemical rockets achieve. Engineers studying Mars missions estimate it could cut transit time within the solar system by many months. The technology has been tested on the ground for decades, though no spacecraft has yet flown with it beyond Earth orbit. Somewhere in the dark, an ember cools without hurry, its glow fading from orange to amber to a hush of gray. There is no need to watch it go out. Let your breathing settle into that same slow fade, each exhale a little dimmer than the one before. The room around you can stay exactly as it is. Nothing here asks anything of you tonight. Sustained power over years, rather than months, is what nuclear electric propulsion offers. It pairs a compact reactor with electric thrusters, generating a steady trickle of energy that can run for the length of an entire mission. Designers imagine it powering probes far beyond where sunlight grows too dim for solar panels to matter. Such systems remain in development, promising endurance where speed alone cannot carry a spacecraft far enough into darkness. Borrowing momentum from a planet has carried spacecraft farther than their own engines ever could. By swinging close to a massive world, a probe can steal a small portion of that planet's orbital energy, gaining speed without burning a drop of fuel. This gravitational assist has become one of the most reliable tools in spaceflight, a way of letting the solar system's own motion do the heaviest lifting. Voyager 1 passed close by Jupiter, then Saturn, borrowing velocity from each in turn. Every flyby bent its path and added speed, a sequence of careful nudges rather than one great push. Without these gravitational assists, the spacecraft would never have reached the edge of the solar system within a human lifetime. The planets themselves became silent partners in its long departure. Near the Sun, in 2018, Parker Solar Probe reached the fastest speed any human-made object has ever achieved. Diving repeatedly through the Sun's outer atmosphere, it used the star's gravity to build velocity beyond 150 kilometers each second. Heat shields shielded its instruments from temperatures fierce enough to vaporize most materials. The mission turned a hostile furnace into an engine of pure acceleration. Physicist Hermann Oberth first described why firing an engine near a massive body yields far more benefit than firing it in open space. The closer a spacecraft is to that gravity well, and the faster it already moves, the more efficient each burst of thrust becomes. Mission planners now use this Oberth effect deliberately, timing engine burns to coincide with a close pass by a planet or star, squeezing extra speed from every drop of fuel. Precursor missions look toward the heliopause, the distant edge where the sun's influence finally fades. Engineers have sketched designs meant to cross that threshold deliberately, carrying instruments built to study what lies just beyond the sun's reach. Unlike the Voyagers, which stumbled into interstellar space almost by accident, these proposed craft would be aimed there from the very start. The goal is simple: to watch the transition happen, not just to have passed through it. The heliopause marks the place where the solar wind finally loses its strength against the pressure of the wider galaxy. Streaming particles from the sun push outward for billions of kilometers, forming an invisible bubble around the whole solar system. At the heliopause, that outward pressure equals the quiet push of gas drifting between the stars. Crossing it means leaving the sun's breath behind entirely and entering the older, colder wind of the galaxy itself. Voyager 2 crossed into interstellar space in 2018, 6 years after its twin. Its instruments recorded a sudden drop in solar particles and a rise in the colder radiation of the galaxy beyond. Unlike Voyager 1, this spacecraft still carried a working plasma instrument, letting scientists measure the crossing directly rather than infer it. Two identical travelers, launched together decades earlier, had each found their own way through the same invisible doorway. NASA researchers have studied a mission called Interstellar Probe, designed purely to look back at the heliosphere from outside it. The concept, developed largely at the Johns Hopkins Applied Physics Laboratory, imagines a spacecraft launched fast enough to outpace the Voyagers within a single human lifetime. Rather than exploring planets, its purpose would be to photograph the sun's entire bubble from a distance, the way a portrait is only understood once you step back from it. Interstellar Probe would aim for a distance of 1,000 astronomical units, a span the Voyagers will not reach for centuries. At that range, the sun would appear as little more than a bright point among countless others. Mission designs imagine decades of travel just to arrive, followed by decades more of quiet observation. The distance itself becomes a kind of instrument, letting scientists finally see the heliosphere's true shape from the outside. Let your jaw loosen now, just slightly, the way it does in the last minutes before sleep. There is no need to hold your face in any particular shape. Let your eyelids grow heavy, heavier than they were a moment ago, until closing them feels like the easiest thing your body has done all day. Behind those closed eyes, there is only a soft, wide darkness, asking nothing of you, holding no shape you need to follow. The Tau Zero Foundation has spent years gathering researchers devoted to the science of interstellar travel. Founded by physicist Mark Millis, a former NASA engineer, the organization supports studies into propulsion methods still decades from any launch pad. Its work rarely makes headlines, yet it keeps a steady body of research alive between the rare bursts of public attention. In quiet offices and shared papers, the idea of reaching another star stays patiently funded, one modest grant at a time. Icarus Interstellar rose in 2009 as the successor to the old Daedalus study, carrying its unfinished questions forward. Founded by physicists Richard Obasi and Kelvin Long, the organization set out to revisit a decades-old design with fresh eyes and better data. What began as a single 1970s blueprint became, decades later, an ongoing conversation among a new generation of engineers. The Starship itself was never built, but the thinking behind it never stopped. Project Icarus set out to redesign the old Daedalus Starship using knowledge that simply did not exist in the 1970s. Engineers revisited its fusion engine, its structure, its fuel assumptions, updating each piece with decades of new physics. The probe they imagined would still be uncrewed, still fusion-powered, still aimed at a nearby star, but built on a far steadier foundation of evidence. It was less a new dream than an old one, carefully repaired. The Institute for Interstellar Studies continues this thread of research today, focused squarely on the physics of propulsion. Founded by physicist Kelvin Long, it brings together engineers and scientists to study fusion, antimatter, and beamed energy as serious, if distant, possibilities. Conferences convene, papers accumulate, and small teams chip away at problems. No single lifetime is likely to solve alone. The work moves slowly, but it moves in the same direction it always had. A 100-year Starship initiative once set out to ask a patient question: could interstellar travel become achievable within a human lifetime of research? Rather than building hardware, it funded studies, workshops, and papers exploring propulsion, life support, and mission design. No spacecraft came from it directly, but it gathered scattered thinking into something closer to a shared roadmap, however distant the destination remained. DARPA, the United States Defense Research Agency, provided seed funding for the 100-year Starship program back in 2011. It was an unusual choice for a military agency, more curious than practical, more philosophical than tactical. The grant helped launch public symposiums where physicists, engineers, and dreamers sat at the same table. For one season, an agency built for defense turned its attention toward the stars. Interstellar travel demands energy on a scale that dwarfs anything used for journeys within our own solar system. Sending a probe to Mars or Jupiter is costly, yet still within reach of existing rockets. Reaching another star system multiplies that cost by staggering, almost unimaginable factors. The distance itself is not the only barrier. The fuel required to cross it remains the deeper challenge. Escape velocity from the solar system exceeds 42 kilometers per second, measured from Earth's distance from the Sun. Any spacecraft hoping to leave the Sun's gravitational grip entirely must reach and sustain that speed. Most missions achieve far less, relying on gravity assists to stretch their fuel further. Even at its edge, the Sun's pull remains a quiet, insistent hand on everything that tries to leave. Voyager 1 moves through the dark at roughly 17 kilometers per second, a speed built from decades of careful gravity assists. It felt swift enough to leave the solar system behind, and in time it did. Yet compared to the vastness ahead, that speed barely qualifies as motion at all. At its current pace, reaching even the nearest star would take tens of thousands of years. Reaching speeds close to the speed of light would require propulsion unlike anything built so far. Chemical rockets, however refined, cannot carry enough fuel to approach such velocities. Physicists studying interstellar travel keep returning to more exotic ideas: beamed energy, antimatter, fusion, each one still theoretical, each one still years from proof. The gap between current engineering and relativistic speed remains wide, though the imagination filling it keeps growing. Let your breath find its own slow shape now, without any effort to guide it. Notice the exhale lengthening, just slightly, each time it leaves you. There is no need to count it, or shape it, or make it deeper than it wants to be. Let it fall where it falls, longer on the way out than the way in. With each release, the body settles a little further into the mattress, the mind loosening its grip on the day, following the breath down into rest. Photon rockets exist only on paper, a concept where a starship would be propelled by its own emitted light rather than expelled mass. In theory, converting all onboard fuel directly into photons would offer the most efficient possible thrust. In practice, the energy required and the engineering to contain it remain far beyond current materials. It stands as one of propulsion's purest ideas, elegant in mathematics, silent in reality. Beamed energy propulsion trades carried fuel for light, sent from somewhere else entirely. A probe fitted with a sail could be pushed forward by lasers or microwaves fired from Earth or orbiting stations. Without heavy propellant tanks, the spacecraft itself could stay remarkably light. The energy source stays behind, shining across the distance, while the traveler simply catches what arrives. Magnetic sails borrow their push from the solar wind, the steady stream of charged particles flowing outward from the sun. A large magnetic field, generated by onboard coils, could deflect these particles like a sail catching an invisible breeze. No propellant burns, no engine roars. The spacecraft simply leans into forces already moving through space. It is propulsion drawn from what the universe was already offering, quietly, all along. A ramjet's promise falters under its own appetite for hydrogen. The scoop, meant to gather fuel from thin interstellar gas, also gathers resistance, a drag that grows as speed increases. Physicists who examined the design found the very particles meant to power the ship might instead slow it down. The concept still lives in textbooks, elegant and unresolved, a bright idea wrestling with a stubborn equation. Antimatter, paired with fusion, could trim the fuel a starship needs to carry. A tiny seed of antimatter, injected into a fusion reaction, might trigger far more energy release than fusion alone provides. Less propellant would mean a lighter craft, and a lighter craft could accelerate more easily. The idea remains attractive, precisely because antimatter is so potent and so rare that only traces have ever been produced. Warp drive, for all its fame, has never left the realm of mathematics. No laboratory has bent space-time. No engine has folded distance the way films imagine. Physics allows the phrase to be written down. Equations balanced and solved, but nothing built has ever demonstrated the effect. It remains a beautiful notation on a chalkboard, admired, unresolved, and entirely theoretical. Miguel Alcubierre, in 1994, proposed a way space-time itself might carry a ship faster than light without breaking relativity's rules. His idea contracts space ahead of a vessel and expands it behind, like a wave carrying a surfer rather than the surfer swimming through water. The ship inside would sit still relative to its own bubble, untouched by the motion around it. The mathematics balances, though nature has never shown such a bubble forming. To hold that bubble open, the Alcubierre solution calls for a kind of energy that pushes rather than pulls, one with negative density. Ordinary matter only attracts through gravity, but this hypothetical form would need to behave in reverse. No material discovered so far carries such a property in any usable, sustained way. The requirement alone keeps the drive comfortably confined to theory. Negative energy, strange as it sounds, has shown itself only in the smallest, quietest corners of physics. Inside the vacuum of empty space, fleeting quantum fluctuations can dip below what we would call zero energy for the briefest of instants. These effects are real, measured in laboratories, but minuscule, and nothing like the vast sustained field a warp bubble would demand. The universe offers only a whisper of the thing an engine would need in abundance. Wormholes, those imagined tunnels linking distant points in space-time, remain shortcuts drawn only in equations. The idea suggests a bridge connecting two far-apart regions of the universe, folding a long journey into a single step through. No observation has ever confirmed one exists, and no experiment has come close to opening one. They persist as a mathematical possibility, admired for their elegance, unconfirmed by any telescope or instrument. Let the weight of the evening settle into your feet first, heavy and unmoving against the sheets. Feel that heaviness rise slowly through the ankles, into the calves, as if gravity has grown gentler with you tonight. Let it climb through the knees, the thighs, the hips, sinking a little deeper into the mattress with every breath. Let the shoulders grow heavy too, and the arms and the hands resting wherever they happen to lie. The whole body settling, layer by layer, into stillness. Einstein's own equations, written a century ago, permit wormhole, like solutions without technically breaking any law of relativity. Physicists Nathan Rosen and Einstein himself sketched an early version in 1935, a bridge connecting 2 points in curved spacetime. The mathematics allows the shape to exist, smooth and consistent, wherever the equations are solved. Whether such a bridge could ever form or survive in the real universe remains an open question physics has not answered. The Casimir effect gives negative energy density a rare foothold in measurable reality. Two uncharged metal plates, placed close enough together in a vacuum, are pushed slightly toward each other by the absence of certain quantum fluctuations between them. Hendrik Casimir predicted this in 1948, and laboratories have since measured the tiny force directly. It is proof that negative energy can exist in nature, even if only at a scale too small to power anything larger than an experiment. A ship crossing between the stars would spend decades bathed in a fine haze of micrometeoroids, grains smaller than sand moving at extraordinary speeds. Even a fleck the size of a grain of rice, traveling fast enough, carries the force of a small impact. Engineers designing such a mission must plan for thousands of these tiny collisions over the years. The hull becomes less a wall than a patient shield, built to absorb what space quietly throws at it. Laboratories on Earth fire particles of dust at extraordinary speeds to see how spacecraft materials hold up. Light gas guns and plasma accelerators launch tiny fragments toward sample panels, mimicking what a real hull might face light years from home. Engineers study the craters left behind, measuring depth and spread to predict long-term wear. It is a strange kind of care, protecting something bound for the depths of space by first wounding its twin here at home. A probe traveling for decades cannot wait for instructions from a planet it left behind long ago. Autonomous navigation lets the craft read starlight, measure its own position, and correct its course without a human hand guiding it. Onboard systems compare star patterns to internal maps, adjusting thrusters in small, careful increments. Out there, patience becomes a kind of intelligence, the spacecraft learning to trust its own quiet calculations. Talking to a spacecraft near another star would ask more of Earth than any mission before it. Current antennas, vast dishes scattered across continents, would need larger arrays and sharper receivers to catch such a faint, distant whisper. Engineers imagine new stations, perhaps built on the far side of the moon, listening for signals thinner than starlight. Every future mission depends a little on this quiet expansion of ears turned toward the sky. Right now, 3 enormous dish complexes stand in California, Spain, and Australia, spaced so Earth's rotation never loses sight of the sky. Together they form the Deep Space Network, listening for whispers from probes scattered across the solar system. Voyager, New Horizons, and dozens of orbiters all send their findings home through these same patient ears. It is humanity's quiet switchboard, always turned toward the dark, always listening for something faint. The farther a spacecraft travels, the thinner its voice becomes by the time it reaches home. Radio signals weaken with distance, the way a shout fades to a whisper across a canyon. Voyager once sent images at a brisk pace. Today its data trickles back at a fraction of that speed. A message that once took seconds to arrive can now take hours, each bit of information stretched thin across the dark. A spacecraft near another star could not wait years for Earth to answer a question. Onboard artificial intelligence might one day choose its own path, deciding when to turn a camera, when to adjust a thruster, when to protect itself from danger. Such systems would need to reason with the same care a human controller once offered from millions of miles away. The mission's judgment would travel with it, held inside its own circuits rather than sent from home. Far from the sun's warmth, sunlight grows too faint to power anything. Radioisotope thermoelectric generators solve this by converting the natural heat of decaying plutonium into steady electricity. No moving parts, no fuel to burn, just the quiet warmth of atoms slowly falling apart. This gentle, decades-long decay has kept probes alive long after they left the light of any star behind. Somewhere beyond the window, a low hum rises and fades, the kind of sound a house makes when it settles for the night. It might be the wind finding a gap in the eaves, or a pipe cooling after the day's use. It comes without hurry, and it leaves the same way, asking nothing of you. Let your breathing match its rhythm, slow and unremarkable, rising and settling like that far-off sound. There is no need to follow it anywhere. Just let it pass through the room, and let yourself sink a little further into the mattress each time it fades. Voyager 1 and Voyager 2 still speak to Earth using the same kind of heat their builders chose in the 1970s. Small blocks of plutonium-238 sealed inside metal casings have warmed their circuits across billions of miles for nearly 50 years. Their power fades slowly, a fraction of a percent lost each year, but it has outlasted almost every plan made for their mission. Two small heat sources, still glowing faintly, carrying two spacecraft farther than any human hand has ever reached. Plutonium-238 does not come easily. Earth's supply was mostly produced decades ago, in reactors built for other purposes, and only a modest amount remains usable for spacecraft. Each gram is precious, guarded, and slow to replace. Future missions bound for the outer dark may need to share this dwindling inheritance or find another way to carry warmth into the years ahead. Beyond radioisotope decay lies a different kind of fire, small nuclear reactors, splitting atoms rather than merely letting them fade, could generate far more power for far longer stretches of a journey. Such reactors might run instruments, engines, even life support, across decades without dimming. Engineers see them as a bridge between the modest glow of old probes and the demanding needs of missions still to come. In the Nevada desert, NASA engineers once switched on a small reactor called kilopower. It ran quietly for hours, proving that a compact nuclear core could produce steady electricity without failure. The test suggested such reactors might one day power a lunar outpost, a Martian habitat, or perhaps a distant, cold destination well past either. It was a small machine carrying a large idea. No propulsion system yet imagined could cross interstellar distances within a single human lifetime. From this limitation comes the idea of the generation ship, a vessel built not for one crew but for many, spanning children, grandchildren, and descendants none of the original travelers would ever meet. The ship becomes a small floating world, carrying an entire lineage toward a star its first passengers would never see. Aboard such a vessel, whole lives would unfold between departure and arrival. Someone might be born in transit, grow old within curved metal walls, and pass their years without ever standing beneath open sky. Their children, in turn, might inherit the same corridors, the same recycled air, the same slow hum of engines. Arrival, if it came at all, would belong to descendants of the ones who first left home. To spare a crew from living out their entire span in transit, researchers have proposed suspended animation, a state where the body's needs are lowered nearly to stillness. Passengers might sleep through most of the voyage, waking only near the destination, using far less food, water, and air along the way. The idea borrows from hibernation seen in nature, stretched toward a purpose nature never intended. Cryonics, the freezing of the human body in hope of future revival, remains far from proven science. No person frozen this way has ever been successfully returned to life, and the damage ice causes to living tissue is still poorly understood. Laboratories continue studying how cells might survive extreme cold without harm. For now, the technology exists more as hope held in reserve than as a tool ready for use. Every drop of water, every breath of air, must be reused aboard a spacecraft far from resupply. Closed-loop life support systems filter moisture from exhaled breath, purify waste into drinkable water, and scrub carbon dioxide from the air before it can build up. Nothing is wasted, because nothing extra can be carried. The ship becomes its own small, careful ecosystem, endlessly recycling what its crew needs to stay alive. High above Earth, the International Space Station has spent years refining these very systems. Machines aboard it capture sweat and breath, turning them back into water clean enough to drink. Oxygen is generated, carbon dioxide removed, and waste carefully managed within a sealed environment. Every improvement made here becomes a small rehearsal for the kind of self-sufficiency a true interstellar craft would one day require. Let warmth begin now at the crown of your head, spreading down like sunlight through still water. Feel it settle into your forehead, easing the small tension there, then drift down through your cheeks and jaw. It moves into your neck and shoulders, loosening what the day left behind, then flows down your arms to your fingertips. Let it pool in your chest, your stomach, your hips, then travel down through your legs to your feet, until your whole body rests inside this slow spreading warmth. Radiation shielding stands among the most difficult problems facing any long-duration voyage. Beyond Earth's magnetic field, cosmic particles strike unshielded hulls without mercy. Engineers study water tanks, layered polyethylene, and even lunar soil as barriers, dense enough to absorb these particles. No material yet offers full protection without adding crushing mass. The search for lighter, stronger shielding continues in laboratories built to simulate deep space's harshest exposure. Cosmic rays carry enough energy to tear through living cells, raising cancer risk for astronauts who spend years beyond Earth's protective shield. Heavy charged particles pass through tissue like tiny bullets, damaging DNA in ways ordinary sunlight never could. Studies of astronauts aboard the space station already show elevated markers of cellular stress. Longer missions toward the stars would multiply this exposure many times over, making shielding not a luxury but a requirement for survival. Rotating a spacecraft slowly could recreate the pull of gravity astronauts lose in weightlessness. Centrifugal force, pressing outward as a habitat spins, would mimic the sensation of standing on solid ground. Without it, muscles weaken and bones lose density month after month. Engineers have studied rotating rings and tethered modules as ways to keep future crews strong enough to walk unaided when they finally reach their destination. Isolation itself becomes a kind of hazard once a mission stretches into years. Small crews confined to metal walls face monotony, friction, and the slow weight of distance from everyone they love. Psychologists studying polar stations and submarine crews have long noted how confinement strains patience and mood. A voyage lasting decades would ask crews to carry not only fuel and food, but emotional endurance across an unbroken stretch of sameness. In the deserts of Utah and the volcanic slopes of Hawaii, researchers have built Mars analog habitats to study exactly this strain. Crews live sealed inside domes for months, rationing supplies and communicating with mission control on deliberate time delays. These experiments reveal how humans cope with confinement long before any real launch occurs. Their findings shape how future interstellar habitats might be designed to protect both body and mind. An interstellar ark would need to be habitat and engine woven into a single design. Living quarters, farms, and propulsion systems would share the same structure, each depending on the other's steady function. Such a vessel would essentially become a small, self-contained world, carrying everything its passengers could ever need across a journey, with no possibility of resupply. Designing one remains largely theoretical, yet the concept guides much of today's long-range mission thinking. Gerard O'Neill, a physicist working in the 1970s, proposed rotating cylinders large enough to hold entire towns. Sunlight would enter through long windows, farmland would curve overhead instead of stretching flat, and gravity would emerge simply from the structure's spin. His designs were meant for orbit around Earth, but they later became a blueprint many interstellar mission thinkers still return to when imagining livable space habitats. A voyage lasting generations would require an ecosystem that sustains itself without resupply from home. Crops would need to grow, waste would need to become fertilizer, and air would need constant renewal through living plants rather than mechanical filters alone. Biologists studying closed biospheres have found this balance difficult to achieve even for short periods. Sustaining it across decades remains one of the deepest unresolved questions in interstellar mission design. Small populations traveling in isolation risk losing genetic diversity across many generations. Without careful planning, related descendants might eventually share too much biology, weakening the crew's resilience to disease. Some proposals suggest carrying frozen genetic material or curating population size deliberately to avoid this drift. The challenge echoes concerns familiar to conservation biologists studying small, isolated animal populations here on Earth. Before any human crew departs, robotic precursor missions could scout a target system first. Small automated probes might arrive decades ahead, mapping planets, measuring radiation, and searching for hazards no telescope on Earth could detect. Their data would let mission planners choose destinations with far greater confidence. In this way, machines would quietly prepare the path long before any traveler ever leaves home. Let your attention rest on something small and drifting, dust caught in a shaft of light, turning end over end with no hurry to arrive anywhere. It rises, it falls, it rises again, never quite settling, never quite lost. Your thoughts can move the same way tonight. Let them turn, unforced in the light, while your breath grows longer and your shoulders sink into the bed beneath you. A single probe carries a single risk, so mission designers have imagined sending many at once. A swarm of small spacecraft, launched together toward the same star, could survive the loss of several without losing the mission itself. If one fails to a stray particle or a broken sensor, others continue onward. Redundancy, spread across many small travelers, becomes a kind of quiet insurance for a very long journey. Coordination among many small probes could make the whole mission steadier than any single machine. Engineers studying swarm behavior look to flocks of birds and colonies of insects, where no single member directs the group, yet the group still moves with purpose. Applied to spacecraft, this could let probes share data, adjust their paths together, and compensate for one another's damage. The mission's intelligence would live in the group, not in any one traveler. Spacecraft have grown steadily smaller, while their capabilities have grown larger. Instruments that once filled entire rooms can now fit inside a hand, thanks to decades of advances in electronics and materials. This shrinking mass matters enormously for interstellar travel, where every extra gram demands more fuel and more energy to move. A lighter probe, launched at the same speed, simply asks less of its journey. Nanotechnology imagines machines built at the scale of molecules, and this could eventually reshape interstellar probes entirely. A device woven from nanoscale sensors and circuits might weigh only grams, yet still gather images, measure radiation, and transmit findings home. Such probes could be launched by the thousands for the cost of a single traditional spacecraft. The vastness between stars may one day be crossed not by giants, but by countless tiny travelers. Three-dimensional printing raises the possibility of building or repairing spacecraft parts while already underway. Instead of carrying every spare component from Earth, a mission could carry raw material and fabricate what it needs mid-flight. A cracked panel, a worn joint, or a replacement tool could be printed on demand, far from any workshop. This kind of self-sufficiency could matter enormously across a voyage, lasting many years without any hope of resupply. Resources gathered along the way could ease the burden of a journey that would otherwise demand carrying everything from home. In situ resource utilization, as engineers call it, means drawing fuel, water, or building material from the environment a spacecraft passes through. A probe might harvest ice from a passing comet or gas from a planet's atmosphere. Refueling en route, rather than departing with everything already on board, could make far longer missions possible. Hydrogen drifts sparsely between the stars, and this near emptiness still holds a theoretical promise. If a spacecraft could gather enough of it while moving, that hydrogen might feed a fusion drive, turning the emptiness itself into fuel. The concept remains largely mathematical for now, since collecting enough atoms from such thin gas is extraordinarily difficult. Still, the idea that a ship might feed on the space it travels through carries a certain quiet elegance. A magnetic sail, useful for catching charged particles to gain speed, could also work in reverse to slow a spacecraft down. As a probe approaches its destination, the same field that once pushed it forward might instead push against the stream of particles ahead, gradually shedding velocity. This dual purpose appeals to mission designers, since carrying separate systems for acceleration and braking would add weight neither journey can easily spare. Reaching a distant star means nothing if a spacecraft cannot slow down once it arrives. A probe crossing space at a meaningful fraction of light speed would need years, sometimes decades, simply to shed that velocity safely, without an atmosphere to brake against. As spacecraft use here at home, deceleration in open space demands entirely new methods still being imagined. It remains one of the most difficult unsolved pieces of any interstellar design. Photons streaming outward from a star could serve as a brake rather than a push. As a spacecraft nears its destination, engineers have proposed turning its sail against the star's own light, letting that pressure slow the craft the way it once accelerated it. The physics works symmetrically in both directions. No mission has tested this yet, but the elegance of using a star's own glow to arrest a ship's speed continues to draw serious study. Let the jaw loosen now, just slightly, as though it forgot what it was holding. There is a small effort behind most faces, unnoticed until it's released, around the eyes, along the brow, across the lips. Let that effort go. Behind closed eyes, there is only dim color, drifting, asking nothing of you. Let the face rest, as if no one were watching it, because no one is. Just this dark, and your breath easing. Choosing where to send a spacecraft depends on two simple questions: how far and how promising. Mission planners weigh a star's distance against the likelihood it hosts worlds worth visiting. A system too far may take centuries to reach even at extraordinary speed. A system too close may hold nothing of interest. The search for a destination is, in many ways, a search for balance. Alpha Centauri A and B shine as near, twins of our own sun, one slightly larger, one slightly smaller, orbiting each other in a slow gravitational dance. Their resemblance to the sun makes them appealing subjects for study, since their light, their heat, their behavior, over time may echo processes astronomers already understand. Any planet circling them would experience daylight not unlike our own. Barnard's star once carried a planet that never existed. In the 1960s, an astronomer named Peter van de Kamp announced he had detected a large world orbiting it, based on tiny shifts in its position across photographic plates. Later observations, using far more precise instruments, found no such planet at all. The claim quietly faded from textbooks, a reminder of how easily faint signals can deceive careful eyes. Barnard's star sits closer to Earth than almost any other star, second only to the Alpha Centauri system itself. A small red dwarf, dim and unremarkable to the naked eye, it drifts through space faster than most stars in our sky, edging its position slightly year by year. Despite its proximity, no confirmed planets have been found there, and its history of mistaken discovery still lingers around its name. Sirius outshines every other star in Earth's night sky, a brilliant white point long used by ancient cultures to mark the seasons. Its brightness comes partly from genuine luminosity, and partly from its relative closeness, a combination that lets it dominate the winter sky. Beside it travels a smaller white dwarf companion, a stellar remnant so dense it defies easy imagination. Tau Ceti resembles the Sun closely enough that astronomers have studied it for decades as a plausible host of habitable worlds. Several candidate planets have been proposed in its orbit, though confirming their nature remains difficult from such a distance. Its stability and sun-like temperament make it one of the more frequently imagined destinations in stories of interstellar travel. Epsilon Eridani hosts a planetary system still shaping itself, young by cosmic standards and surrounded by rings of dust that have not yet settled into finished worlds. Astronomers view it almost as a window into what our own solar system may have looked like billions of years ago, when planets were still gathering material and finding their orbits. Wolf 359 became a battlefield only in fiction, though the star itself is entirely real, a faint red dwarf lying among the nearest stars to Earth. Writers borrowed its name for dramatic effect, staging an imagined conflict there precisely because it sounded close enough to matter and distant enough to feel otherworldly. The true star, meanwhile, continues its quiet existence, unaware of the stories told about it. Reaching Alpha Centauri at even a fraction of light speed could take decades, and slower designs stretch that span into centuries. A generation ship, a robotic swarm, or a laser-driven sail would each carry a different span of waiting stitched into its journey. Time itself becomes part of the payload, measured not in hours, but in human lifetimes folded across the dark between stars. Every mission design forces a trade between velocity and the cost of reaching it. Pushing a probe faster demands exponentially more energy, so engineers weigh shaving away years of travel against the practical limits of fuel, mass, and power. The fastest path is rarely the cheapest one, and every proposed voyage becomes an exercise in choosing which sacrifice to make. Let your exhale grow a little longer than your inhale, and let that be enough for now. Breathe in for a count of 4, then release for 6, feeling the air leave slower than it arrived. Each breath like this settles you further into the mattress, into the dark, into the hush of this hour. There is only this rhythm, the rise, the longer fall, the pause before the next one begins. Light itself could become the messenger between a distant probe and home. Laser-based optical communication can pack far more data into a beam than traditional radio waves, offering the promise of clearer images and richer signals across vast distances. A single narrow beam of light, precisely aimed, might carry more information than a wide radio dish ever could. NASA tested this idea directly with a mission called the Laser Communications Relay Demonstration, launched to prove that optical links could work reliably in space. Engineers watched data stream between orbit and ground stations at rates far beyond older radio systems. The demonstration marked an early step toward the kind of communication a future interstellar probe might one day depend on. Entangled particles behave in ways that still puzzle physics, linked across distance in a manner that seems to defy ordinary signaling. Researchers have explored whether this strange connection could someday carry information between spacecraft and Earth. So far, physics itself withholds any way to use entanglement for sending a message, and it remains a theoretical curiosity rather than a working technology for the stars. A giant shade, flown far ahead of a telescope, could block a star's glare precisely enough to reveal the faint planets hiding beside it. Engineers have proposed flying such a star shade in precise formation with an orbiting observatory, its shape sculpted to cancel out diffracted light. If it works as designed, it could let astronomers see an exoplanet directly, not merely infer its presence through indirect clues. Even with such tools, capturing a direct image of a planet remains extraordinarily difficult. A star's brightness can outshine its planets by billions of times, burying any reflected light in overwhelming glare. Only the most advanced telescopes, paired with careful shielding or masking, manage to catch even a faint pixel of a distant world. The James Webb Space Telescope has begun reading the chemistry of worlds beyond our solar system, passing starlight through their atmospheres to reveal traces of water, carbon dioxide, and other molecules. Each spectrum becomes a kind of fingerprint, sketching what a distant sky might actually contain. It is a patient, careful kind of listening, done not with sound, but with light bent through unfamiliar air. A habitable zone is not a fixed ring around every star. It shifts with how brightly that star burns. A dim red dwarf pulls its zone close and narrow, while a blazing giant pushes livable distances far outward. Luminosity, more than distance alone, decides where liquid water might survive on a planet's surface, redrawing the boundaries of possibility star by star. A biosignature is any clue chemistry leaves behind when life is present. Oxygen paired with methane, in the wrong proportions to occur naturally, could hint at living processes cycling gases through a planet's air and water. No single molecule proves the case alone. Researchers look instead for combinations that are hard to explain any other way. Patterns chemistry alone rarely produces on its own. Beyond biology, a technosignature would point to intelligence rather than microbes. Astronomers describe hypothetical clues like waste heat from vast structures, unusual light patterns from orbiting arrays, or chemical traces industry might leave in an atmosphere. None have been confirmed. The search widens what counts as evidence, listening not just for life, but for minds that build things. The search for extraterrestrial intelligence, known simply as SETI, listens for radio or light signals that might carry the fingerprint of another civilization. Vast dish antennas sweep the sky night after night, gathering whispers from stars that may hold nothing at all. Decades of listening have returned silence so far. Still, each scan adds another patch of sky quietly ruled out, another small certainty carved from uncertainty. Let the weight of your body settle now, deeper than before. Feel your feet grow heavy first, sinking into the mattress like stones set down after a long walk. That heaviness rises slowly, through your calves, your knees, pooling in your thighs like warm sand. Let your hips sink, your back sink, shoulder by shoulder, releasing its grip on the day. There is nowhere lighter to be than exactly here, resting under its own gentle weight. Breakthrough Listen, launched with private funding, has turned some of the world's largest telescopes toward 1 million nearby stars, scanning for radio and optical signals that don't belong to nature. It is the most thorough search of its kind ever conducted. The project sifts staggering amounts of data, hunting for a signal shaped less like static and more like intention. Physicist Enrico Fermi once asked a simple question over lunch: if the galaxy is old and vast, where is everyone? Billions of years and billions of stars should have given rise to civilizations long before ours. Yet the sky offers no confirmed voices, no visitors, no evidence at all. The gap between what seems likely and what has actually been found is called the Fermi paradox, and it remains open. In 1961, astronomer Frank Drake wrote an equation to organize the guesswork around alien life. It multiplies together things like the rate of star formation, the fraction of planets that could host life, and how long a civilization might broadcast before falling silent. Every term remains uncertain. The equation offers not an answer but a frame for thinking clearly about how much we still don't know. Beyond listening, a handful of projects have chosen to speak. Deliberate signals, encoded with mathematics, images, or music, have been aimed toward specific stars, carrying something of Earth outward on purpose. These messages travel at the speed of light, patient and silent, arriving decades or centuries after they leave. No reply has come. None was expected soon. In 1974, the Arecibo radio telescope in Puerto Rico beamed a message toward a cluster of stars called Messier 13, some 25,000 light-years away. Encoded in simple binary, it described numbers, dia the shape of a human figure, and the telescope that sent it. The star cluster it aimed for won't even be in that same position by the time the signal arrives. It was less a message meant to be answered than a gesture, offered outward into deep time. METI International, founded in the 2010s, argues that listening alone may never be enough, that someone must eventually choose to speak first. Its founders design and send intentional messages toward nearby stars, believing contact requires initiative as much as patience. Others in the field worry that announcing our presence carries risks we can't fully weigh. The debate itself reflects something tender in us, the wish to be found, matched by the caution of being unsure who might be listening. Contact with another civilization raises questions that reach beyond physics. Would a message change how humanity understands itself? Could contact bring danger as easily as wonder? These questions have no laboratory to test them in, no experiment to settle them cleanly. Philosophers, ethicists, and researchers keep turning them over, aware that an answer, if it ever comes, might arrive with no chance to negotiate its terms. Some scientists have warned against broadcasting Earth's precise location into the dark. Stephen Hawking once suggested that announcing our presence to unknown listeners might carry risk without any guaranteed reward. Others consider this caution overstated, built on fear rather than evidence. No civilization has ever answered a signal we've sent. Whether that silence means safety or simply distance remains unresolved. Funding for a true interstellar mission remains almost entirely theoretical. Agencies study concepts, publish papers, sketch propulsion designs on whiteboards, but no government has committed the sums such a voyage would demand. Estimates for even a modest probe run into the trillions. For now, interstellar travel exists mostly on paper, in equations and diagrams waiting for technology or resolve to catch up. Private companies have begun investing where governments once worked largely alone. Aerospace firms now fund research into propulsion methods once confined to academic journals, from refined ion drives to nuclear concepts revisited after decades of silence. Their motives blend curiosity with commerce, but the effect adds resources to a field long starved of them. Progress once bound to government budget cycles now moves, at times on private ambition. Somewhere beyond this room, a low hum rises and fades, like wind moving through a distant hallway. It doesn't ask to be followed. Let it pass through you, the way night air moves through an open window, arriving without demand, leaving without a goodbye. Your breath can match its rhythm if it wants to, or simply keep its own pace, unbothered, while the dark settles a little deeper around you. SpaceX's Starship, still being tested, aims to make heavy launches routine rather than rare. If it succeeds, the cost of lifting mass into orbit could fall far enough to support fuel depots, orbital factories, and staging platforms once thought unaffordable. Cheaper access to space, doesn't guarantee an interstellar journey, but it lays the groundwork such a journey would eventually require. Reusable rockets have already cut the price of reaching orbit by remarkable margins. Boosters that once fell into the ocean now land upright and fly again within weeks. Each reused flight spreads the original cost across more missions, turning what was once disposable into something closer to a fleet. The change required no new physics, only patience with engineering many once dismissed as impractical. Outposts on the Moon and on Mars could serve as waypoints rather than final destinations. Fuel drawn from lunar ice or Martian resources might refill tanks before a longer voyage begins, easing the burden of carrying everything from Earth. Such bases remain unbuilt, but their logic is simple. Journeys outward may work best in stages, resting at each foothold before reaching for the next. Asteroids hold metals, water, and volatile compounds that could one day become raw material for building spacecraft far from Earth's gravity. Mining them in place would avoid the cost of launching every component from the ground. No mission has yet extracted resources at scale, but the idea reframes asteroids as more than drifting curiosities. They become supply depots scattered through the dark. Laser infrastructure powerful enough to push a light sail toward another star need not appear all at once. Smaller arrays could be built first, tested on modest targets, then expanded panel by panel as funding and confidence grow. What begins as a tool for nearby missions could, added to over years, become the engine for something far greater. Nothing about it requires a single leap, only accumulation over time. Reaching another star may never be the work of one nation alone. The instruments, the launch infrastructure, the decades of tracking and funding all favor cooperation over competition. Space agencies already share data across borders for missions far closer to home. An interstellar effort, spanning generations, might only hold together if the whole species carries it forward, not one flag alone. No one can say when the propulsion breakthrough will arrive that finally makes deep space feel close. Physics has surprised its own experts before, turning theory into hardware faster than expected, or leaving promising ideas stalled for decades. Fusion drives, antimatter engines, laser sails, each waits on discoveries that cannot be scheduled. Progress in this field tends to arrive sideways, not on command. Even with steady progress, true interstellar travel may remain a project measured in centuries rather than years. The distances are simply too vast for shortcuts to appear quickly. A journey that takes decades with today's fastest spacecraft would need speeds far beyond anything yet built. Patience, more than urgency, may be the defining trait of whoever eventually makes the crossing. No date exists yet for humanity's first true probe, bound for another star. Every mission discussed so far, from light sails to fusion concepts, remains a proposal rather than a launch. The honest answer is that the timeline depends on funding, physics, and will, none of which can be predicted with certainty. What is certain only is that the question remains open, waiting for its answer. Across every age, from the first charts of stars to blueprints for light sails, one thread has stayed unbroken, the wish to reach farther than before. It carried ancient navigators across oceans and later carried machines past the edge of the solar system. That same wish rests quietly in you tonight, needing nothing from you now but rest. The stars will still be there tomorrow, patient as always. Sleep well, and let the wondering wait for morning.